Okay, we're coming into the home stretch with the Langevin equation and lecture set 2. We've learned some things. We've learned about a deep connection between the randomness in a random walk and the existence, or the posited existence by Langevin, of this viscous or frictional loss or dissipation term in the equation of motion. They seem to work together with one another. But we did it in an approximate way, right? We assumed this constant ensemble average v squared. And if you thought that was a cheat, then we'll see a way of fixing that, and we'll see that in the end it wasn't that much of a cheat. But we did neglect the real statistical nature of these random forcings. So we should do that now in a better way. And the way to do that is to go back to the formal solution, that integrating factor solution to the original Langevin equation. We mentioned it before, but here it is again. You know, it's just applying that integrating factor method, which can't be boiled down to a simple solution because of the random stochastic nature of the f of t, right? It's always going to be expressible as an integral over f of t. Okay, there it is. Well, again, if we just take the ensemble average of that solution, we get back the old solution to the simplified version of the Langevin equation, right? There's an initial push V naught in some direction. That's going to be damped out by the viscosity, but then that's it. That's all the simple linear version of the expectation value of V gives us. We've totally gotten rid of the fluctuations. But, well, I think you can see where we're going with this. What we really want is the time dependence of the expectation value of V squared. And that's, again, the expectation value of V dot V. You can't just separate that out into two expectation values because V is very strongly correlated with itself. So we have to bite the bullet and take this expression at the top and put that into this V dot V. And when we multiply that out, there are a bunch of nasty looking terms, but it's really just a quadratic expansion of something times itself, right? The first term is really just the ensemble averaged zero order solution with no fluctuating components whatsoever. So you've noticed I've even gotten rid of the angle brackets for the expectation value because it is its own ensemble average. There's nothing fluctuating in that term. But if you were to repeat the experiment a million times and just look at that component of the velocity, it would be the same in every one of those simulations. It's the other components that contain the randomness. Okay, well, I'll put that back up at the top. And now the second term is something we have to look at. I can argue for that term being zero because there's only one f in it, right? Strictly speaking, the ensemble average is over that entire thing. But really what we can do is collapse that ensemble average just onto the f itself. I mean, V naught is not something that varies randomly, and the 1 over m is not something that's random. The integral over time, well, if we were taking a time derivative, df dt, we knew it was fair to take that ensemble average and put it right in because the differentiation operator is linear and ensemble average is just a big old sum. Same thing with integrals. The integral is also a linear operator, and you can do that same thing. So really, you can just take that the angle brackets and put them right on the f, and we know the angle bracket, the ensemble average of f itself is zero. So that whole second term vanishes. All right, we're left with the third term. The third term is something we call the autocorrelation of the f. Notice there's two integrals there because the single solution for vector v had an integral. So if we have to multiply two of those integrals together, it's sort of like taking a double integral over two completely independent time dimensions that I'm calling t1 and t2. So we're taking f as a function of t1, f as a function of t2, and basically looking at every possible combination of the product of f at all those first times and all those second times. And that's what we really mean by the autocorrelation. You might have seen it in signal processing or statistics courses. What it really means is that we're doing this integral that I'm calling I, and I'm also now taking advantage again of the fact that the integration operators are linear, so I've taken the angle brackets and put them as far in as possible to only be acting on the stochastic random variables. But now there's two of them. It's f evaluated at one time, dotted into f evaluated at another time. Mathematically, or maybe physically, it's more interesting it's more insightful to redefine the variables rather than having to always think about two separate times at two different random times in this time sequence. Let's keep the t1, but let's change the t2 to something that involves the difference between t2 and t1. So that's what this s variable is. We call it the time lag, right? So we're integrating over t1, but then at each of those t1s, we're starting there at that t1, and we're looking at all the times to the future and the past. That's what we're calling s, the time lag, and we're comparing f at those with the time with the value of f at t1. So you see, I've had to change the integration limits and the integrand with the exponential there. But now this quantity is something that makes more sense to think about, and I'm calling it A of S, the autocorrelation of F, because that lag S is really the primary variable that we have to worry about, right? Right, it's a function of this relative time lag between these two random times sampled in the time sequence. Now, strictly speaking, that A should have also depended on T1, but in a way, we can argue that it really shouldn't depend on T1, because the function f itself is just this random sequence that goes on and on and on forever. So what we pick for T1 really shouldn't make any difference, right? Because that randomness should look the same if we picked T1 to be here or if we picked it to be here. No matter where, the randomness is going to look the same. But it really does depend on the time lag, right? Because, and I'm sort of showing what it should look like here on the left. At a time lag of 0, that means you're taking f and you're multiplying it exactly by itself with no time lag. So if you're multiplying it by itself, then you're multiplying each value by itself. If it's positive, it's two positives. If it's negative, it's two negatives that make a positive. So the sum over all that, over all the different expectation values in the average, should be some strong positive number, because when f is correlated with itself, that's a very high correlation. At other times, well, maybe it's not so strongly correlated because it's random, right? If each step in that randomness that I often draw is how can I say it? If it's a Markov process like we talked about before, if each step is completely uncorrelated with the previous steps, then if you do the experiment millions of times, there should be no correlation between f at one time and f at a different time, right? So that's where I'm saying that rapidly as s gets above 0 in either the positive or negative directions, it should the autocorrelation should rapidly go to 0. And of course, it's symmetric because there's really nothing special about jumping forward in time and comparing to f here, or jumping back in time and comparing to f here. So it should be symmetric around around s positive and negative as well. I can show you some other examples. I found some plots from a statistics GitHub site that sort of showed some examples. You know, if there's some smoothness to the random noise, where if you just take a small step forward, it's still slightly correlated with itself because there's some smoothness. There could be some shape to the correlation, but the more random, the more rapidly randomly fluctuating the things get as you go to the blue curve at the bottom. The only time you're going to have a non-zero correlation is when it's autocorrelated exactly with itself with 0 lag. And that's really what we're talking about. The autocorrelation should look something like the bottom right blue thing, which is kind of like a Dirac delta function, right? So here we're now talking about these fluctuating forces from the collisions with the water molecules, and if that's happening very, very rapidly compared to other times that we care about in the system, like the viscous damping time tau, then why don't we just make this completely uncorrelated assumption and assume that the autocorrelation function is a Dirac delta function. Okay, yeah, no correlation between any subsequent impact events that give rise to the randomness. So another way of saying this, I mean, whenever we talk about Dirac delta functions, they're never usually useful completely by themselves. They're only useful when we take integrals over them, right? That's the actual real result from them. So maybe the way to define this A naught coefficient out front here really should just be to say that A naught is defined as the integral under the autocorrelation curve. In other words, we don't really care about the shape of the curve, we just care about its integral, because as you see from the solution, we have to take an integral over it. So yeah, so it's very sharp, and we're not really caring too much about its actual width or height, but it's really just the integral under the curve that we care about. Right, so that's what we have to do now. We have this integral that we want to compute. The A of S is now essentially a delta function, and if we work that out, you can go through the math, right? If this is a delta function, then you're just evaluating the rest of the integrand at S equals 0. That's what we get here, and remember to take out the A naught out front. So that's the inner integral here that we've just performed, kind of trivially because it's a delta function. But now there's an outer integral. There's a function of T1, and you have to integrate over T1, so you can do that. And now we actually get a solution for the ensemble average of V squared, which is a function of time. And it's a function of time because we have this arbitrary initial condition V naught. And we also have this specified A naught, which is finally now a place where we've encapsulated the statistics of the random fluctuations. Yeah. Right, so there's that solution. And well, we can also go back to our previous thoughts about Maxwell-Boltzmann statistics, right? As t goes to infinity, we still kind of want to ensure that the physics of the randomness, as we've talked about it as a thermal speed or a temperature, is sort of still there. And we do see that as time goes to infinity in the solution, there is a constant term that survives. And it's this second of the three terms here. Right, it's just these constants out front with a 1. So, right, we know as t goes to infinity, the v squared approaches that solution. So why don't we just call that the square of the thermal speed like we did before? So this is a much more general way of thinking about the solution, where now instead of assuming that the v squared ensemble average is constant over all times, all we're doing now is saying that there's this constant that it eventually approaches once it forgets about the initial condition, and that's what we're now thinking about. So now what does this mean? We now have a way of comparing three quantities. We can compare the A naught, which we've defined. We can compare that with the temperature, which comes from the thermal speed, and notice in there's also the tau, the viscous decay time. This is called the Fluctuation-Dissipation Theorem. I'm calling it sort of a strong version of the Einstein relation that we talked about in the previous video. Now we're not expressing it as a diffusion coefficient, but we're explicitly now saying that there's a relationship between three of these parameters in the problem, right? Prior to this point, we were really just treating the A naught as an arbitrary thing and the tau as an arbitrary thing, but they're not completely arbitrary. If we know the temperature of the system, then we're not free to specify those other things. Yeah, that's the key insight to take away here. Now that we can look at the dependencies and understand a few things, right? We see that holding everything else constant, A naught is proportional to temperature, which makes sense because A naught is in some way a measure of the amplitude of the F, right? If the F amplitude was much bigger, then the A naught would be bigger. And our intuition tells us that should also mean a higher temperature, a hotter gas or fluid. But I guess the way to think about this is that if we completely specify the micro processes, right, both the temperature and the A naught, the properties of the random forcing, that uniquely allows us to solve for the tau. It allows us to completely specify this macro viscous or frictional dissipative force. And that's really why we were doing all this, right? It tells us that these so-called transport processes, viscosity, friction, also heat conduction, electrical resistivity in a resistor, all these things are are emergent properties that come up out of small scale randomness. And if you specify the small scale randomness, you specify the macro dissipative properties. Right. Oh, so there's also ways that you can take this v squared solution as a function of time and actually plug it back in to the ensemble averaged Langevin equation. Remember, that had the 2v squared on the right-hand side. We can plug that time dependence in and resolve that second order differential equation for r squared. And here are some example solutions of that. The solution for v squared as a function of time is on the left, and you can see by definition that as time goes to infinity, we've our solution of v going to v thermal squared is imposed. So our initial assumption in the previous video that v squared was equal to a constant v thermal squared is the black curve, and now we're just showing with the different colors what you get with different initial conditions, and eventually those initial conditions get forgotten about. But now you take these velocities, plug them into the ensemble average Langevin equation, and you can see, well, it's sort of similar, right? At initial times, it's still sort of parabolic, so it's r squared going as t squared, ballistic, and then at later times, it turns into diffusion, r squared going as t, so it's really the same kind of thing. I guess the last thing I wanted to say was just to, again, talk in a little bit more of a philosophical way about why this is important. And I have this sort of evocative paragraph from Patria and Beale's book that I think you can also get this excerpt in PDF on the website. You know, they say that the most striking feature of this is that it relates the fluctuations of a physical quantity pertaining to the equilibrium state, right, the temperature, to a dissipative process, which in practice is realized only when the system is subject to an external force that drives it away from the equilibrium, right? The only time that you should really care, for example, about the excuse me, about the viscosity, either slowing things down or speeding them up, is at these early times, right? At these early times when you haven't yet approached the thermal equilibrium at V thermal. But those out of equilibrium times are deeply connected to the properties of the randomness that gives rise to the equilibrium state. That's really the key here. And in fact, you know, going all the way back to Langevin saying, there must be two forces. There's a viscous force and a random force. That was so necessary because these two things are so deeply connected, as we've now seen. And this paper by Ramshaw actually explores what happens if there was just the random F force without the viscous force. That would actually be a disaster. That would actually produce a never-ending rise in the random motions. It would be this irreversible and continuous heating of the system. So the viscosity is sort of needed because it's generated by the randomness, but it's needed to counterbalance this ever growing randomness. It's a lot to take in, but I hope it makes some sense. And in the coming lectures about astrophysical plasmas, we'll be coming back occasionally to these ideas to see how they're important for measurable quantities. Okay.